Right now, a machine floating 1,000,000 miles from Earth is staring at a single point of light in the constellation Leo. That point is so faint, your own eyes could never find it. Even most telescopes on the ground struggle to hold on to it. But this is not most telescopes. It is the most powerful eye humanity has ever built. And for years, it has been quietly pulling secrets out of that tiny point of light. Secrets about a planet. More than 100 light years away, a planet warm enough for liquid water. A planet that some scientists believe may be covered by a single ocean deeper than anything that has ever existed on our world. And in the spring of 2025, scientists announced they had detected something in that planet's atmosphere that, on Earth, is produced almost entirely by one thing: life. Headlines exploded within hours. Had we finally found it? Had we found proof that we are not alone? Here is what most of those headlines never told you. Here is what happened after the cameras turned off, because the real story of this planet is far stranger, far messier, and far more important than the version that went viral. It is a story about the most promising world we have ever found, a scientific battle that played out in public, and a discovery still unfolding right now in 2026 that almost nobody is talking about. I am your host, and this is your channel. If stories like this are the reason you're here, subscribe now, because we are only just getting started. Let's start at the beginning. In 2015, a crippled but still functioning space telescope named Kepler was running an extended mission called K2, staring at thousands of stars at once, while watching for the faintest possible dimming whenever a planet crossed in front of its star. In that flood of data, astronomers found something orbiting a small, dim red star. They cataloged the planet as K2-18b. At first it was nothing special, one entry among thousands, no press conference, no headline. But this quiet little world had three properties that would eventually place it at the center of one of the biggest scientific arguments of our time. First, its size. K2-18b is roughly 8.5 times the mass of Earth and about 2.5 times as wide. That makes it what astronomers call a sub-Neptune, a category of planet that simply does not exist anywhere in our own solar system. We have small rocky worlds like Earth and Mars. We have giant gas worlds like Jupiter and Neptune. We have nothing in between. And it turns out the galaxy is packed with these in-between worlds, worlds we barely understand at all. Second, its orbit. K2-18b circles its star once every 33 days. Around a star like our Sun, that kind of orbit would be a death sentence, a slow roast far too close to the flames. But K2-18's star is a red dwarf, smaller, cooler, and dimmer than our Sun. Around a star that faint, a 33-day orbit lands the planet squarely inside the habitable zone, the narrow band of space where temperatures allow liquid water to exist rather than boiling away or freezing solid. Third, and this is the detail that changed everything, K2-18b transits its star from our exact point of view in the universe. That single cosmic coincidence means we can do something that sounds almost impossible. We can read the chemistry of its atmosphere from more than 100 light years away. Here's how. When K2-18b passes directly in front of its star, a sliver of starlight filters through the thin shell of atmosphere wrapped around the planet before continuing its journey toward Earth. Every molecule in that atmosphere absorbs light at its own specific wavelengths, its own chemical fingerprint. If you can catch that starlight and split it apart with enough precision, the gaps tell you exactly which gases that light passed through on its way to you. Think about what that actually means. Light that left a distant star more than a century ago traveled across empty space for over 100 years, brushed briefly through the sky of an alien world, and only then fell into a telescope built by human hands. Hidden inside that light, in a code written in shadows, is the chemical recipe of another planet's air. That is not science fiction. That is a measurement we can genuinely make. In 2019, the Hubble Space Telescope made the first attempt and reported what looked like water vapor in K2-18b's atmosphere. The first time water had ever been reported on a habitable zone planet outside our solar system. It put this quiet little world on the map. But Hubble was never built for this kind of precision work. And some scientists argued the signal could just as easily have been methane. The planet was keeping its secrets. To crack them open, humanity needed a bigger key. That key launched on Christmas morning, 2021. The James Webb Space Telescope is the most ambitious scientific instrument ever. Built, a gold-coated mirror more than 6 meters wide, folded like origami to fit inside its rocket, unfurled 1,000,000 miles from Earth, and cooled by a sun shield the size of a tennis court. It cost roughly $10 billion and took a quarter of a century to design and build. Hundreds of mechanisms had to unfold perfectly in sequence, with no chance of repair if something went wrong. Every single one of them worked. In 2023, a team led by Niku Madhusudan at the University of Cambridge pointed this machine at K2-18b, and the fog that had surrounded the planet for years finally began to lift. The results were striking. Methane, clearly present. Carbon dioxide, clearly present. It marked the first time carbon-based molecules had ever been confirmed in the atmosphere of a habitable zone exoplanet. But just as important as what Webb found was what it did not find. Almost no ammonia. And that absence is itself a clue, because if this planet were simply a ball of gas all the way down, ammonia should be visible high in its atmosphere. Something beneath the clouds seemed to be quietly stripping it away. One explanation is as strange as it is beautiful. An ocean. A planet-spanning sea of liquid water, sitting beneath a hydrogen-rich sky, silently absorbing ammonia out of the air above it. Scientists have a name for this hypothetical class of world. A Hycean planet, hydrogen plus ocean. A world with no continents, no islands, no land at all. Just water stretching from horizon to horizon, wrapped entirely around the planet beneath a permanent amber twilight. If life could take hold in a place like that, it would have evolved in conditions we have never even come close to simulating here on Earth. And this matters far beyond one single planet, because sub-Neptunes like K2's 18b are not rare. They are the single most common type of planet the galaxy produces. Our own solar system just happens to have skipped them entirely. If worlds like this really can hold liquid oceans, then the number of potentially habitable places in our galaxy doesn't just grow a little, it explodes, from a handful of Earth-like twins to potentially billions of ocean worlds hiding in plain sight. Buried in that same 2023 dataset was something else, a faint, uncertain whisper of a molecule called dimethyl sulfide. The signal was weak, far too weak to claim anything with confidence. Most researchers set it aside, but the Cambridge team did not, because on Earth, dimethyl sulfide is not produced by volcanoes, lightning, or rock chemistry. It is produced almost entirely by life, specifically by microscopic marine plankton drifting through our oceans. That faint smell of the sea on a beach walk is partly this exact molecule, the breath of a living ocean. So the team requested more telescope time, switched to a different instrument sensitive to different wavelengths, and waited for the planet to cross its star again. What came back in April 2025 exploded across the world. The new data showed signs of dimethyl sulfide, or its close chemical cousin dimethyl disulfide. And the concentration was not subtle. The numbers suggested amounts thousands of times higher than anything ever measured in Earth's own atmosphere. If real, this wasn't just a hint of life. It suggested an ocean absolutely saturated with biological activity on a scale far beyond anything our own seas have ever produced. Researchers called it the strongest hint of possible extraterrestrial life ever detected. For a few days, that spring, millions of people around the world genuinely wondered if humanity had just found its neighbors. If a sentence like that doesn't make you want to hit like and subscribe, I don't know what will. But stay with me, because the story is about to get far more complicated. Now here is where it matters to understand exactly what that announcement meant, and where it didn't. The original claim was pinned at a confidence level scientists call 3 sigma, meaning there was roughly a 3 in 1,000 chance the signal was pure noise. That sounds convincing. But in physics and astronomy, the gold standard for declaring an actual discovery is 5 sigma, a false alarm chance of about 1 in 3.5 million. 3 sigma results collapse all the time. The Cambridge team knew this and said so publicly, estimating that only 16 to 24 additional hours of telescope time might be enough to settle the question for good. Then, before anyone reached that finish line, the rest of the scientific world got to work tearing the data apart, which is exactly how good science is supposed to function. Extraordinary claims attract extraordinary scrutiny. Cracks appeared fast. One independent team reprocessed the same observations with slightly different, equally valid statistical methods, and found that in most of their runs, the dimethyl sulfide signal simply faded away. Another group compared the data against a library of hundreds of different molecules and discovered that other, far more mundane chemicals could fit the same spectral pattern almost as well. At the level of precision Webb can currently reach on this planet, dimethyl sulfide and something as ordinary as ethane can look nearly identical. Then came a twist nobody expected. In 2024, scientists analyzing data from the Rosetta space mission found dimethyl sulfide on a comet, a frozen, lifeless chunk of ice and dust. It has since turned up drifting in interstellar gas clouds, in the empty space between stars where nothing lives at all. Laboratory experiments even showed the molecule can form through pure ordinary. Chemistry under exoplanet-like conditions, no biology required whatsoever. The one molecule that had been called a smoking gun for life turned out to have a perfectly innocent, non-living explanation. By late 2025 and into 2026, the picture had sharpened further and not in the direction the headlines wanted. A major NASA-led reanalysis, combining every instrument and every observation of the planet, concluded there simply wasn't enough evidence to support a confirmed biosignature. A more recent independent study pushed the confidence for the dimethyl sulfide signal down even further, to around 2.7 sigma, still tantalizing, but nowhere close to proof. When researchers surveyed the astrobiology community directly in 2026, only a small fraction, somewhere around 6 or 7%, agreed that scientists had probably found actual signs of extraterrestrial life on this planet. And in March 2026, a separate team ran one of the most sensitive searches ever attempted for signs of technology, radio signals, industrial byproducts, anything that might suggest intelligent activity anywhere in the K2-18 system. They found nothing. That last sentence deserves a moment. An advanced search for alien technology around this exact planet came back completely empty. If that doesn't earn a like and subscribe from you, nothing will, but don't go anywhere, because the story genuinely does not end there. Because while the internet argued over one contested molecule, the telescope kept watching, and what it confirmed next may matter more in the long run than the entire Biosignature debate. A separate team at NASA's Jet Propulsion Laboratory pointed Webb at K2-18b across several more transits, measuring its atmosphere with more precision than ever before. The results were unambiguous on several fronts. The methane is real, confirmed well beyond doubt. The carbon dioxide is real, and when researchers modeled what kind of planet could produce exactly this kind of atmosphere, the answer was genuinely stunning. K2-18b appears to be a true water world, not a dry ball of rock, not a miniature gas giant, but a planet so drenched in water that it could make up a significant fraction of its total mass, according to some estimates, reaching into the double digits as a percentage of the planet's entire weight. Stop and actually sit with that number for a second. Earth, our own blue planet, the water world of our solar system, is only about 0.02% water by mass. Every ocean you've ever seen, every storm, every glacier, is a thin, damp film wrapped around a ball of rock. K2-18b may be soaked in water on a scale we barely have language for. Oceans, potentially hundreds of times deeper than our own, wrapped around a hidden interior we still don't fully understand. The scientists leading that particular study put it plainly. This confirms K2-18b as our best chance to study a potentially habitable environment beyond our solar system. Not a maybe. Not one candidate among a dozen others. The single best opportunity we currently have. Now, in fairness, here is the other side of the ledger, because a planet-wide ocean is only good news if it's the right kind of ocean. The same models that allow for a warm, welcoming sea on K2-18b also allow for far darker possibilities. If the planet's clouds don't reflect enough starlight back into space, the surface could be scorching, and instead of a gentle liquid ocean, the water might exist as supercritical steam, a crushing, blistering state of matter that is neither truly liquid nor truly gas, and almost certainly hostile to any chemistry resembling life as we understand it. Some researchers argue the planet may not have a clean surface at all, or could conceal a churning ocean of molten rock rather than water. And looming over everything is the star itself. Red dwarfs are notorious for violent temper tantrums, lashing out with flares and radiation, and K2-18b sits far closer to its star than Earth does to the Sun. Whether life could realistically survive under that kind of sky remains one of the biggest open questions in modern astronomy. It's worth pausing here to understand just how young this entire field of science actually is. The very first planet ever confirmed orbiting a normal star beyond our own sun was only detected in 1995, barely 3 decades ago. Before that, humanity had no direct evidence that any other star in the universe hosted planets at all. We assumed they probably existed somewhere out there, but assuming is not the same as knowing. Since then, astronomers have confirmed more than 5,000 exoplanets, an entire hidden universe of worlds that simply didn't exist in our data 30 years ago. And out of those 5,000 plus confirmed worlds, K2-18b currently sits near the very top of the list of places worth watching closely. Not because we're certain it's alive, but because it's one of the very few planets small enough, close enough, and positioned well enough for us to actually study its atmosphere in meaningful detail at all. Most of the 5,000 other planets we found are simply too far, too faint, or oriented. The wrong way for this kind of chemical analysis to even be possible. That scarcity is exactly why K2-18b keeps pulling astronomers back again and again. It also helps to understand why the Technosignature search from March 2026 mattered so much, even though it came back empty. A Technosignature search isn't looking for microbes or chemistry. It's specifically looking for evidence of intelligence, structured radio transmissions, unusual heat, patterns that might suggest industrial activity, anything that wouldn't occur naturally. The team behind that 2026 study didn't just glance at the data and shrug. They built one of the most sensitive and systematic search frameworks ever applied to a single planetary system, checking an enormous range of possible signals across the K2-18 system. Coming up empty doesn't prove there's nothing there. Space is vast, technology could be silent, and our instruments still have real limits. But it does tell us that if anything resembling an advanced civilization is broadcasting from that system in an obvious way, we haven't caught it yet. Combined with the biosignature debate, it paints a picture of a planet that is scientifically rich, but nowhere near confirmed as inhabited by anything, simple or advanced. So no, we have not confirmed a fully, unquestionably habitable planet, whatever a headline might promise you. What we have confirmed is something science has genuinely never had before. A world sitting in the habitable zone with an atmosphere we can actually read, carbon-based chemistry we can actually measure, and a massive water inventory backed by real data, not guesswork. Every previous candidate for habitability was essentially an educated guess based on size and distance alone. This one we can actually interrogate, and that is exactly why what happens next matters so much. Right now, in 2026, K2-18b remains one of the single most valuable targets in the sky for the James Webb Space Telescope. Every time it crosses its star again, that's another chance to catch that century-old starlight and squeeze a little more truth out of it. A single additional day or so of dedicated telescope time could be enough to either push the dimethyl sulfide signal up to the gold standard 5 sigma threshold or kill it for good. Either outcome would be genuinely historic because for the first time in the entire history of our species, the question, is there life on that planet, is no longer pure. Philosophy. It is a measurement with a price tag, a schedule, and a machine already sitting in position to attempt it. Webb will not be working alone for much longer either. The European Space Agency is preparing a mission called Ariel, designed to survey the atmospheres of hundreds of exoplanets at once. NASA is developing something called the Habitable Worlds Observatory, a future telescope built for exactly one purpose written directly into its name, to search nearby planets specifically for the fingerprints of life. K2-18b is, in many ways, the rehearsal. It is where astronomers are learning, molecule by molecule and mistake by mistake, exactly how to read an alien sky correctly, so that when a real, unambiguous signal eventually does appear and survives every possible test, we will know, without argument, exactly what we're looking at. There is one more thing worth carrying away from this story. When the dimethyl sulfide claim began cracking under scrutiny, some people called it an embarrassment, a failure. It was the opposite. A tentative signal was floated. The entire global scientific community attacked it from every conceivable angle. Weak evidence was correctly identified as weak, while the solid discoveries, the methane, the carbon dioxide, the enormous water-rich interior, survived every single test and came out stronger for it. That is not science failing. That is science working exactly as it's supposed to, out in the open, in real time, on the biggest possible question there is. The planet did not get less interesting once the initial headlines faded. It got more interesting, because now we know with far greater precision exactly what we're looking at. A warm, water-soaked world more than 100 light years away, still holding at least one final secret behind a curtain we already know how to open. The light carrying that answer left this planet's sky long before you were born, and right now it is streaming into a golden mirror a million miles above your head. The only real question left is what it's going to say once we finally, fully decode it. If this is the kind of story that keeps you looking up at night, subscribe right now and turn on notifications. Because the moment the next results from K2-18b land, this channel is going to break them down before almost anyone else does. Drop a comment and tell me what you honestly think. Is that ocean empty, or is something actually swimming in it? And share this video with someone who still thinks we're completely alone out here, because the answer to that question might be closer than any of us realize.